Okay, guys, welcome. Today we're going to talk about function transformations and how they relate to graphs. So the previous video we discussed how to do some basic graphs. We're going to talk today about how graphs are affected if we do certain operations to them, right? So if you have a function and you do a certain transformation, how does that affect the graph of the transform graph? All right, so we're going to talk about vertical transformations. So if we're going to either shift a graph up or down, or stretch or compress a graph across the horizontal axis, or flip it over the horizontal axis. And then we'll also talk about horizontal function transformations where we either shift it left or right, stretch or compress it horizontally, or flip it across the vertical axis. All right. And then, of course, we'll talk about how do you do more than one of them at a time. Another thing that we'll talk about is how does transforming a function affect the domain and range of the function. And then we will do sort of application of these function transformations, which is how to classify even and odd functions. All right. Now, I believe for most of this section, we're going to look at the graph of f of x's x squared on the domain from x is negative 1 to positive 1. And of course, the range, if you restrict your domain to negative 1 to 1, would become 0 to 1, right? So if you're not familiar with this graph, I would suggest that you make yourself familiar with it. It's one of the most common graphs that's used for demonstrational purposes in many different topics in math. And of course, we're going to use it today to talk about graph transformations. Okay, now, first of all, we're going to look at something like we're taking our f of x, which again, throughout f of x is x squared, and we're going to add 1 to it. All right, so again, f of x is x squared, and the domain of f is in the interval of negative 1 to 1. All right, now if you're adding, so you have g of x is f of x plus 1. All right, so you still have x going in and something coming out, right? So in other words, your x is not affected. Right? So neither is your domain. Your domain is still negative 1 to 1. All right, but remember that f, this is part B now, so part A, the domain is still negative 1 to 1. All right, for part B, we have that, remember, f has range 0 to 1. Right? Now, G has a range of whatever is happening to F, but now we're adding 1 to it, right? So that means that G has the range. So if F lowest point was 0 and we add 1 to it, that new lowest point is now 1, right? And if its highest point was 1 and we add 1 to that, its new highest point is now 2. So we have that G has a range of 1 to 2. All right, so now what does a graph of this thing look like? So a graph would look something like this, right? So I'm going to put the original f here. So our original f was like this, right? So, and again, we're just talking about it from negative 1 to 1. So it looks something like this. All right, now the domain is still negative 1 to 1, but we've shifted everything up by 1 unit. So I'm going to get something like this for G, right? So this blue one is G. And of course, that's f of x plus 1. And this green one is just f of x. Right? So it looks like if we added 1 to it, it shifted it up by a unit of 1. All right. Now what happens here? Well, now we're doing something similar, except now we're subtracting 1. All right. So we should expect that the domain is still unchanged. So the domain is still -1 to 1. But for part B, we want to find the range of h. We've taken the range that we've had, which was 0 to 1, and we're shifting everything down by 1. So this should become -1 to 0. Right? And then, of course, part C will sketch the graph. Now, again, the original was like this. So this is my f of x. But now in the new one, we've shifted everything down by 1, right? So this is now here. This is now here. This is now here. We have something like this. All right, so this is h of x. All right, so we're getting to the idea of what is meant by a vertical translation, right? Or shifting a graph up and down. So if you have a function and you add something to it, that means that you're shifting it up by a units, right? So if you're adding a number, that's a shift up. And of course, if you subtract a number, that's a shift down. Right? And that's the most basic type of transformation, is if we take a function and we simply add or subtract a number from it, you're shifting the graph up or down, all right, depending on the sign of a. Okay, now let's look at another example. So again, we now have g, which is 2 times f of x, and h, which is 1/2 times f of x. Now again, for the same reason, we're not altering our x values going in, right? If I plug in -1 into f, it's still equivalent to plugging in a -1 in g, and the same for h, right? So in part A, your domain is still going to be -1 to 1. That's not changing. All right, but now in part B, for the range of g, you're now taking your domain, or sorry, your range, which is y equals 0 to y equals 1, and you're multiplying those each by 2. So in G, you're now having y equal 0 times 2 is still 0, but 1 times 2 is now 2. So now your range for G is 0 to 2. Right? And then sort of similarly, if you look at H, you're taking 0 and 1, but you're multiplying them by 1/2 this time. Right? So now H, your lowest point is still 0, but your highest point is now 1 times 1/2, which is 1/2. So your range here will be 0 to 1/2. All right, so now let's put all these on here. So again, just as a reference, let's put our original on here. So again, we have that x squared looks something like that. All right, now if I multiply everything by 2, my highest point is now 2, but I still have this 0 here, so I'm doing something like this now. All right, so I'm kind of stretching it out a little bit. And now, of course, on the other hand, if I am making it go to 1/2, I'm going to have something that looks like this. So I'm sort of compressing it down, or you can think of stretching it wider, right? So this, of course, this red one is h, which is 1/2 x squared, right? This blue one was g, which is 2 times x squared. And then this green one was the original f of x, which is x squared. Right, so you can see that by multiplying by a number out front of your x squared, it looks like you're going to sort of affect whether or not the graph is like skinnier or wider, is sort of one way you could think of it. All right, and then the way we think of this as is that if you have a number out front, this C here, right, that's basically stretching the graph vertically by a factor of C, right? And I put a little note here. When you think of C being less than 1, like sort of up here we had C being equal to 1/2, it's better to think of it as, instead of stretching it, you're shrinking it or squashing it down, right? So if you have that C is like a fraction between 0 and 1, then you're squashing it or shrinking it, whereas if it's bigger, you're stretching it. Okay. So again, let's look at, so now we're throwing a negative in front of our F. And in this case, so again, part A, you are not changing your domain, still negative 1 to 1. All right. Now part B, your original range was 0 to 1, but we're now throwing a negative in front of everything, right? So this will still be a 0. Let's put it this way, actually. So you have y equals 0, y equals 1, right? Now, if you put a negative in front of each of these, you're going to get y equals negative of 0 is still 0. But now negative of 1, you get y is negative 1. So, of course, we need to order this from lowest to highest. So we're going to say negative 1 to 0 is our range. Okay, so let's look at this graph. So if we draw the original, of course, that's going to look something like this. And now I need to instead make it go from 0 to negative 1, right? So both of these points here are going to become a negative 1, and the 0 is still in the middle, right? And you get something like this. All right, so essentially it's flipping it over this axis, right? And that's what the negative out front is going to do. Another way that you can think of it is that you're taking every x or every y value and you're then getting its negative y value in the new one, right? And what this really means is that if you toss a negative out front of your function, that's going to be found by flipping the original graph over the horizontal axis, right? So that's essentially what's happening there. Okay, now let's take a look at what happens when we're sort of messing with the inside. Okay, now here's where the domain is going to be different now. All right, so domain is definitely different. So the domain of F was negative 1 to 1. All right, but now the domain of G is basically found by whatever x value is going in is whatever x value you plugged into F, but add 1 to it, right? So now I need to take, let's see, let me put it this way. Okay, so x value going into G is an x value into F added to 1. Right, so you sort of have this relationship where you have a gx value is equal to an fx value plus 1, right? So in order to get your g, and maybe I'll put a little subscript here, let's say that's g, and let's say that's f, right? So what you need to do is you need to take your xf values and you need to subtract 1 from them, right? So what this really means is that if your domain for f was negative 1 to positive 1, well, I need to take my f values and I need to subtract 1 from them in order to get my G values. So this is actually going to be now from -2. So if I take -1 and subtract 1 from it, I'm going to get -2. And then if I subtract 1 from 1 from 1, I'm going to get 0. All right. Now, it turns out that in this case, the range is not changing. So the range is still 0 to 1. And let's go ahead and look at the graph. So now the original of course is going to look like this. That's the original f. Okay, and now when I add 1 to my sort of my x components in the f version, right, I need to subtract 1. So now I'm going to have this is going to move over here. This one, so let's see, that one moves there. This one moves this way. I get this. And now you have something like this. All right, so this shifted it left by 1. Okay, so this actually sort of works the opposite way, right? Because when you look at this, you have this +1 in here, right? So common logic would suggest that if you're affecting the if you know you're affecting the domain, a +1 you would think would move you to the right, right? But it actually works the opposite. So if you have x plus b, that's going to shift you left by b units, right? And if you have x minus b on the inside, that's going to shift you to the right, right? And it sort of works out because of that, sort of setting those x values equal to each other in that relationship. Okay. Now, what happens if we multiply on the inside now? Okay, so again, we're definitely going to affect the domain. So part C, we'll just say the range is still 1 to 1. Okay. Now, if we're finding our gx values found by multiplying fx values by 2, then it looks like our G domain, instead of -1 to 1, will be -2 to 2. Right? And then similarly, our hx values will be -1/2 to 1/2. Right? And let's just see. So, right. So it's going to, oh, wait a minute. You know what? I think I need a similar argument here. These should be reversed. Right? So just like before, this means, for example, that you have a gx value is equal to an fx value times 2. So then to get the original g value, you need xg over 2 is equal to fx, or I should be xf. Right? So your g will go from -1/2 to 1/2. And your b would be the -2 to 2 version. Okay, so let's take a look at what this looks like. So our original looks like this. Okay, and now our other one will be, so from -1/2 to 1/2, so we're going to have something like this. All right, so this is our g, which was f of 2x. Right, and this was our original f of x. And then last but not least, h of x we now have from -2 to +2. All right, so this is h of x, which is f of 1/2 x. All right, and that's sort of the idea there. So that leads us to stretching a graph horizontally, right? So if you have that, so if your C is bigger than 1, this is sort of the idea here. If your C is bigger than 1, that's really shrinking the graph. So that's what you saw up here, right? Because this G was f of 2x, but that's making the graph smaller, right? That's that middle one here. And then if you have 1/2, then that means that you are actually making the graph larger. All right, so that's another one that sort of works maybe the opposite way that you would think. Okay. One last one here. So now to make this a little bit different, we're now just considering the domain from 1/2 to 1. All right, so just keep that in mind. Now, for the domain, for f, it was -1, or sorry, we're assuming 1/2 to 1 this time. Right? So if I take the negative of each of those, that means that my new domain is now -1 to -1/2. Right? If I take the negatives of each of those and reverse it, I'm going to get -1 to -1/2. Now, of course, the range is not going to change. Well, I guess in this case it will. So if I square 1/1/2, I'm going to get 1/4. And if I square 1, I'm going to get 1. So it looks like my range is going to be 1/4 to 1. All right, so now for a graph, here's what we'll have. So the original, right, since we're just going from 1/2 to 1, it's going to look like this solid part here, right? So this was my original f of x. And now if I look at g, which is the flipped version, I'm going to have this part of it, right? So what this suggests is that if you toss a negative on the inside this time, you're getting a flip across the vertical axis, right? And what you can do is you can find the domain of g by multiplying each number in the domain of f by -1, which is sort of what we did here. Okay. So now what we would do if you want to do more than one of these is you essentially, you apply the transformations in the same order as how the operations are applied to the corresponding function, right? So for example, what's happening to f here? Well, first, it's being multiplied by -2, and then add 1, right? So this is just where you sort of use your order of operations here, right? So first of all, what's the domain of g? Well, we didn't mess anything on the inside of our f here, so the domain is still -1 to 1. But now for part C, what do we do to the range? Well, the original range was -1 to 1. And then we multiplied everything by -2. So that's now going to make the range -2 to +2. And the negative is also going to flip the horizontal axis. And of course, the +1 at the end shifts everything up. So it looks like our new range is going to be, if I add 1 to -2, I'm going to get -1. If I add 1 to 2, I'm going to get 3. Okay, so what's this graph look like? Well, the original will look like this. And then I stretched it by a factor of 2. And then I flipped it, and then I also shifted everything up 1. So it looks like I'm going to get something like this. So we're going from 1 to 3. So we should get something like this. All right, so again, the negative would flip it over, the 2 would stretch it, and then I'd have to shift everything up by 1. So it looks something like that. Okay. Now, this one is sort of slightly different because what's happening here you're shifting it up 1 first. And then multiplying by -2. All right, so again, we didn't mess with the inside of f, so the domain is still -1 to 1. But now the range, if I start at 0 to 1, if I shift it up 1 at 0 to 2, and then if I multiply everything by -2, I'm going to get, let's see, so from a -4 to 0, right? So that's my range. Okay, so what does this graph look like? Of course, so it's a little bit different. So here's the original again, just for reference. And then if I shift it up 1 first, and then multiply everything by -2, I'm going to get something, let's see. So I should get something like this. All right, so that would shift everything up 1 and then multiply by -2. Okay, so that's that combination. And now we can talk about an application of a bunch of these function transformations, and that's the idea of identifying an even function, or at least the first one is identifying an even function. And what this essentially means that if I replace x with -x, I'm going to get the same thing back. All right. Or another way you can think of it is that a graph is even if it's the same thing when you flip it across the vertical axis. All right. So let's look at an example of this. All right. Now this one is sort of an easy one. So we're going to show that if f of x is absolute value of x, that it's even. All right. So what happens if I do f of -x? That's the absolute value of -x. All right, but what does absolute value do to any number? It just makes it positive. All right. And if I look at f of regular x, so I should say this. This gives you x, right? And I guess let me leave that back. Because if x is negative, then that's a separate thing. But of course, f of x is also absolute value of x. So since these are equal, that means that this is an even function. All right. And then on the other hand, we have that a function is odd if the negative essentially comes out front. All right. And this means that a function is odd if it's unchanged when you flip it across the origin, or you can think of it as when you flip it across both axes. All right. So we're going to show that if we have f of x is 1 over x, that's an odd function. Right? So if we replace this with -x, we get 1 over -x, which of course you can write as 1 over x with a negative out front. All right? So that means if you combine these two, that if you take the negative out front of the f of x, that you're going to get f of negative x. All right, so that means that this is an odd function. Right, and that's sort of the idea. All right, so that concludes this section on function transformations. I hope you enjoyed, and I will see you next time.